All right, guys, welcome. And today we're going to debunk science. But Amir, you're a chemical engineer. Don't you love science? Yes, I do. But to really love something, you kind of get intimate with its flaws, don't you? So today we're going to be exploring the flaws of hypertrophy or muscle growth research across the board. And the reason I wanted to make this video is because the evidence-based community online has really split themselves into camps on a lot of key issues, right? Or key issues, right? But low volume versus high volume, so less sets or more sets. Do we stretch the crap out of every muscle or do we not stretch it at all? Do we train to failure, not train to failure? And the list goes on, right? And on either side of these camps, you have people pulling up studies and being like, look, this is why I'm right and you're wrong. So I want to explore the shortcomings of the evidence, right? Because that leads to a more in-depth knowledge. And at the end of the day, if you want to come to your own conclusions about this stuff, you have to know where research can go wrong. So through this video, I'm going to go through a step-by-step process of pretty much how a study gets conducted from A to Z, and at every step in that process where error can be introduced. So without further ado, let's get right into it. Step number one for literally any study is get participants involved. And there are a lot of logistical issues in doing this. I mean, think about it. You're trying to convince people to show up to a lab multiple times a week for about an hour or two. So how do you get them to do that? Money. Right? So funding is another limitation we'll have to talk about, but you only have so much money to pay these people, and it's generally hard to convince people to do it in the first place. So because of that, sample size, which is how many participants in the study, is generally low. And the lower your sample size, the less confident you are that the results that you get actually apply to the general population, and conversely, the larger your sample size, the more certain you are that this will extrapolate to the general population. So low sample size, no bueno, okay? And along a similar line, the duration of the study. So again, let's put our real life hats on for a second. These are generally carried out at universities. So whatever study that has to be done kind of has to fit within a semester. So that's why generally 6 to 12 weeks happens, and 12 weeks being pretty long. But we know that in real life, we consider muscle growth and the long-term adaptations, and it occurs over years. The shorter the duration of the study, the more that we neglect the long-term adaptations that could be happening due to the protocol. All right, so the shorter it is, the worse it is, and they're generally pretty short, okay? So that is another place that we can generally go wrong. Especially considering, if it's only like 4 weeks long, neural adaptations are still at play. So that's a different topic though. All right, next we have trained versus untrained subjects. It's usually one or the other. If you have a mixed bag of subjects, your study is in a really ugly spot because you can expose untrained and trained people to the same exact stimuli, the same exact workout, and their responses will be completely different. If you take a noob versus a gym veteran and put them through the workouts, their response will be completely different. So this is something that has to be a consideration, right? What may reflect great results in an untrained population may not necessarily indicate a good workout or a good recommendation for the trained population, and vice versa. Right, so again, another big thing to take into account when you're thinking about who am I trying to make recommendations for. All right, and the last thing is external factors, right? Because realistically, we only have these people in the lab for an hour or so, a few times a week, and we have no idea what they're doing outside. We could tell them eat 200 grams of protein. We have no idea if they're doing that, right? So, diet will significantly impact their results. Are they sleeping? Are they stressed out? Do they have an exam? A lot of these subjects are college students because it happens at a university. And if we're working with a trained population especially, right? I'm talking about my gym freaks who just love it, right? are they working out outside the recommended protocol that we're working with? Because that will, diminish their capacity for recovery and could alter the results. So these are all problems that you can run into with group selection that may alter, the outcome of your study. So let's move on. Now we get into the fun stuff, protocol design. How do we design the workouts to either prove or disprove our hypothesis? Okay, so first consideration is volume. Is it too much or too little? Now, depending on who you ask, the two very different sets of answers, okay? But to illustrate my point, let's travel to the extreme ends of the spectrum. Let's say we're trying to determine the effectiveness of a leg extension versus squat, right? If I have my subjects do 300 sets of squats per week versus 300 sets of leg extensions, I think that's too much to ascertain which is better for growth. I think at that point we would be figuring out which can you recover from better, if that's even possible at that point. Or on the other end of the spectrum, is it too little? Are we doing one set of leg extensions or squats every 3 to 4 weeks? Probably not enough of an effect or a stimulus to have any effect, okay? So important consideration, oftentimes kind of botched, but a little bit harder to ascertain if this one was botched. This one, on the other hand, intensity is closely related to volume. So what you set the intensity at, whether this is appropriate, really depends on intensity, right? But reps in reserve is a measure of intensity. It says how many reps short of failure you stopped. So 1 rep in reserve would mean you left 1 rep in the gas tank. You stopped 1 rep before you would fail that movement. 2 reps in reserve means you stopped 2 before failure, and so on and so forth. So it's very dependent on the subject's ability to gauge what their reps in reserve count is. So something to keep in mind if you're looking at the reps in reserve of the study, you're like, did they really train to 4 RIR or 3 RIR? Well, I don't know. They don't know either. Okay, so this is talked about, volume's talked about a lot. This is kind of talked about. Range of motion, this is kind of not talked about as much, at least this aspect of it, and this kind of scares me a little bit. Let's say we're talking about a bench press, right? And the exercise scientist, and honestly the general population might be like, yeah, full range of motion is touching the bar to your chest. For who, right? It's highly dependent on the individual's anatomy, right? Like if you take someone who's 6'5" and has really weird proportions of their arms, super long arms, right? And you tell them to touch the bar to their chest, that bar's, and let's say they have a thin rib cage too, in terms of distance and the angle of their shoulder, right? They can be going through a huge range of motion touching the bar to their chest. And then someone who's kind of short and squat and has a really thick rib cage, good power lifters, right? They can be boop, right? Those are 2 very different sets of work in terms of energy and stimuli to the muscles. So if you arbitrarily set the, touch the bar to your chest, that's full range of motion, depending on the individual, that can be very different things and that can drastically affect the outcomes depending on that individual, right? So range of motion considerations. And then I really never see this talked about in studies that use machines specifically. The resistance profiles of the machines. And I think this is something that exercise scientists, they're not physicists, so they don't really take mechanics into account, but not all machines are built the same way. Like let's take a hamstring curl machine, for example, right? And let's say these are my feet over here, here's my knee, right? So this is a seated hamstring curl machine, right? So here's my leg, right? And screw it, let's use my leg, okay? If I choose a machine where it has a ton of resistance up here and it is a very low resistance down here, that's a good thing because my hamstrings are very strong up here and pretty weak as I flex my knee, okay? So it matches what my hamstring is capable of. Let's say I flip that on its head. Let's say I took a machine and the way it's designed is that it's super easy up here and then really difficult down here. 5 reps with the same weight stack on there is completely different in terms of stimulus, right? The resistance profile of a machine is everything to the stimulus. Never talked about. Never. and it's something that needs to be talked about, right? So this can drastically affect the outcome of the study. If you have a crappy machine, of course the alternative is going to be better. Okay? Food for thought. Almost forgot to say that this is just the tip of the iceberg. I mean, off the top of my head, rest periods, right? That's another thing that can greatly affect the outcomes. But the most important thing that I did forget to mention was, do they even report this stuff? Do they report the RIR, the range of motion that they defined, what they defined the point of failure as, what machine they used? A lot of times, they don't report a lot of things. So how are we supposed to draw conclusions about it? So, more food for thought. Both before and after you put your subjects through the protocol, you have to collect data, right? And these are the ways to assess and quantify muscular hypertrophy, muscle growth, okay? First up, we have biopsy. Now, this is a super accurate method. You actually take a chunk of the muscle from the subject. You can look at the cross-sectional area and the fiber types and all that good stuff and determine at a cellular level, did hypertrophy occur? And if so, how much? But turns out people don't like getting cut. So, doesn't happen that often, and it's also pretty expensive. So we're just gonna put a $ slash a little drop of blood, and more looks like water because the blue marker, but you get the idea, right? Next up, we have MRI. Again, a great tool. You can get a 3D image of the muscle and you get all these different cross sections from different angles. We could nerd out over it. Yay, it's great. Except the fact that it's really complex and time consuming and also very expensive. So money sign, and I guess time, but time is money, so money sign. Okay. DEXA and ultrasound. These are a lot more common. So we'll start off with the DEXA scan. The DEXA scan can scan your whole body. It could roughly segment it, like left arm, right arm, trunk, left leg, right leg, things like that. But it can't actually differentiate between muscles. So that's kind of a problem with DEXA. But the bigger problem, I'd say, is that it measures lean mass. So under the umbrella of lean mass falls muscle tissue, which good, we want that. But also bone, other tissues, and water. So if you're in a really hydrated state, it can throw the DEXA off. And if you're in a really carb-loaded state, because glycogen will hold water molecules, also will throw the DEXA off. So a lot of false readings on that. Ultrasound is kind of a finicky one. It can be great, but a lot of times there's a lot of considerations to ultrasound. Right? So ultrasound measures muscle thickness. So let's say if we have, a bicep, right? And let's just say this is an arm, boom, okay? It has to get measured, and let's say this is the bone, this little dotted line, okay? So the ultrasound basically gets put here, gets rubbed on here. So it's just that thickness, the thickness measurement. And it's highly dependent on technician skill and using the same technician the whole time, right? Because you have to apply it at precisely the same point, both before and after. And on top of that, with how much pressure you apply will change the measurement, right? So if I push hard into my bicep, all of a sudden that's a smaller distance as compared to if I lightly press on it. So it's very dependent on the technician to get accurate readings. Furthermore, right, if you have a pump, or let's say after the pump goes away, you have muscle swelling and edema, right? The muscle will actually be a little bit thicker just because of inflammation, right? So not necessarily muscle growth. And also, again, kind of the same thing as DEXA. If you're in a really carb-loaded state, and maybe you weren't carb-loaded before, then you can get a falsely big measurement on it. So there are problems with ultrasound. Last problem with ultrasound is that we're only looking at muscle thickness, but oftentimes the muscle will grow in different areas. The overall volume of the muscle will grow, but maybe it didn't grow right here, right? So that's something, again, to keep in mind. But levels of inaccuracy can be introduced, or error can be introduced with this method. And then circumference measurements with like a tape. Guys, on a lot of these studies, we're looking at like fractions of an inch, often fractions of millimeters. So taking a measurement tape and going, it's not going to really be an accurate method at all. It's better than nothing, I guess, but this is kind of a crapshoot. But yeah, you can kind of see how the most commonly used ones have large sources of error in terms of, just how they work really. But let's move on to the last thing, statistics. Meatheads, hold on, I'll make this simple, okay, don't leave. But this is how we actually analyze the results and, figure out what's significant and what's insignificant, okay? So it's a game of statistics and definitions, but I'll just touch on these briefly. So first of all, I alluded to earlier, we're working with small sample sizes. The smaller the sample size, the less confident you can be that your results are in fact true of the population, okay? Another thing is statistically significant does not mean practically significant. Based on your P levels and confidence levels and whatnot, let's say in a leg extension versus squat, in one of the quadriceps muscles, the leg extension had 0.45 more millimeters of growth, or even, let's say, a smaller fraction of a millimeter, right? Based on how you kind of set up your experiment and definitions, that could be statistically significant, but in practice, do we really care about 0.2 millimeters? Probably not. For all intents and purposes, it probably could be the same, especially when you factor in all those errors we just talked about. So yeah, that's something to keep in mind, especially in the conclusion section, right? So rather than just looking at if it was statistically significant, take an actual look at the effect size, which is the magnitude, which is the 0.2 millimeters or whatever it might be. Okay. Another problem with the stats is the variance and just the variability between individuals. Like you can subject two individuals to the same exact protocol and they might have vastly different responses just due to genetics and all the other factors, right? So that's kind of a problem when you're playing this game of stats. Another thing is reporting. A lot of the data isn't really reported, and I touched on that earlier, so I won't go too deep down the rabbit hole there, but this is an important one that doesn't get talked about a lot. This is publication bias, okay? So if a group of researchers sets out to prove something, they're like, let's say you have a bunch of researchers who love squats. They love squats, and they're comparing a squat versus a leg extension for quadriceps growth, and they find no difference between them. It's not a very sexy headline. There's not a statistically significant headline there. So oftentimes those just vanish into non-existence. They don't get published because they're not sexy. When in reality, this is important data that we should be, that we can be using, right? So we don't see all the studies that have been done. We just see the ones that are deemed sexy enough to make it into a journal. So, all of these kind of point out some of the errors in the data analysis. And the last thing I want to talk about is how, the average person or content creators or whoever looks at these studies. Gen pop analysis, okay? So this is how people who aren't expert researchers actually look at these studies a lot of the time. And this includes some of your favorite YouTubers, okay? So they'll read the title, very great, sexy, attention grabbing, right? And maybe they'll read the introduction even, right? Nice little optimistic outlook on the study. And then once things start getting hairy, right, the methods and data and graphs and numbers, who wants to look at that? It's boring. Scroll right to the conclusions. And that is a grave mistake because the conclusions lack all of the context that can be found in the methods and data. All of those things we talked about are methods and data. Okay? So if you're only reading the conclusion, and again, the statistical significance that we discussed, sometimes the conclusion will highlight statistical significance when, practically speaking, it's not very significant at all, right? So you can oversimplify really complex topics when you just read the conclusions, okay? And I used to be guilty of this at one point when I first started reading research, right? I was like, oh, they know what they're doing, just skip. But no. All of the understanding is found in the methods and data. You should try coming to your own conclusions before reading the author's conclusions. That's my take. Okay? But here's a good kind of rule to abide by, for the most part. Beware of those speaking in absolutes. And if somebody draws absolutes from uncertain experiments, you may think twice about taking that advice. I made this video not to discredit hypertrophy research as a whole, but to better understand its limitations so we can better apply it to real-world training. It should be used as a tool, as a piece of the puzzle, alongside other areas of exercise research, such as biomechanics, anatomy, physiology, as well as personal experience, so that we can best help the people that need to be helped. That is all. Much love. Hope you enjoyed.